1,400 meters of altitude.
That's surprising. You want to stand here. Just used to standing more on the left side because I'm.
You know that
Where were you located before you came here? Iowa State. Iowa State. Did you know a guy there named Long Fuchs? Maybe he was in the James lab. Oh yeah, I was in physics. I was in physics. That's the solid state physicist point of view. But when you're in the physics department, you're not doing solid state physics, you don't see the names of people.
you know, I can't get used to this.
Have you been in
Yes.
This shot is the University of Texas, and also really looks very architecture. Building the main tower at the top part. Right. So we don't have the big side on it.
It's not exactly Stalinist architecture, but the bottom of the
There, yes, after. But as you look up there, it's like, oh, tall, very tall, brick side building, purple on top, very cool.
You see that there's a
No, you can't do it. Yeah, well, the style. Pretty, not very like Chicago style, but glass.
well, it's definitely not a very southern architecture. It doesn't strike me as something in San Diego or something. It's kind of usually. It's almost like Grand America.
Just square.
Grand America Hotel. Yeah, with that style. They try to be
it's like 2 to 1. It's a little too much. I have not been.
Mark was telling me it's late time.
And I promise I won't say anything about our lunch conversation. Well, it's too late.
Or you feel like, oh, maybe someone will disagree with you, and then you have
Let's get started. Thank you for being here. It's my pleasure to be introducing Mark Raizen today from the University of Texas at Austin. Told me that it is at Austin, it's not in Austin, we don't know why. I never met Mark before. I got in touch with him on a suggestion by Michael because Mark has been publishing some tests of Maxwell-Boltzmann statistics in Optical Chapter. That's the type of things that he does in his lab. He addresses very fundamental questions, many of which have to do with cooling atoms. And today he's telling us about a technique involving magnetic field for this cooling that he's developing.
Thank you very much. It's a pleasure to be here. I've had a very enjoyable day talking to colleagues, making new friends. I'm also excited as a Trekkie to be sitting on the bridge of the USS Enterprise, as I understand, which I did not expect to be in Salt Lake City, but as it turns out. Today I will tell you about Maxwell's demon, which you perhaps have heard about in your thermodynamics class. But what I want to show you is that Maxwell's demon actually is alive and useful. Can be used to cool atoms and even to do something even more useful, which is separating isotopes, which could save our lives. And so the first part will be about cooling, the second part about isotopes. But let me start with this man who needs no introduction to a physics audience, James Clerk Maxwell, perhaps the greatest scientist ever. Einstein had a picture of him on his mantle and considered him one of the greatest scientists, if not the greatest, unified electricity, magnetism, and light. But towards the end of his life, Maxwell died fairly young. He was only 48. But he was interested in the basics of thermodynamics and the understanding the second law of thermodynamics and specifically. And he came up with a thought experiment. These thought experiments are useful in physics because they make us think. And this one dates back to 1871 and is known as Maxwell's demon. Actually, the name was not given by Maxwell, but by his friend, Lord Kelvin. And Maxwell apparently didn't like the name because it sounded kind of spooky. And Maxwell, but what Maxwell had in mind was, could there be a way around the second law of thermodynamics in the following sense? Consider gas particles bouncing around in a chamber, and the chamber is divided into two parts, A and B. And if we just had a hole between the two, then we would expect these to thermalize. For example, if you started with all particles on one side, they would establish an equilibrium, a pressure equilibrium, where they would be equally distributed on both sides. But Maxwell asked the following question. Suppose you had a creature, he called it a creature with deft hands, who could see the coming and going of every particle in this box with this magic flashlight here, as you see. And if he saw a particle coming towards a trap door, he would open the door and let the particle through. Otherwise, he would keep it closed. And in such a fashion, Maxwell argued that you could cause all the particles from part B to move over to part A without ever doing any work on the particles. Now that would appear as a violation of the second law. And this caused endless debate. For 140 years, people debated, because you can ask with every thought experiment, what's the flaw? Where's the catch? Could this be done? You know, maybe it could be done in principle, but could it be done in practice? And so, really, people have felt very strongly about it. So much so that some people would argue that if you believe in this, then you probably believe in that. And maybe some of the people in the audience do, and if so, I apologize. But what I want to try and convince you in this talk is that this thought experiment actually can work, but not exactly as portrayed in this fanciful picture, which is appropriate for Halloween, which is coming up. So that's my task, and I will get to that a little bit later in my talk. But now, let me move to a very specific system that we are considering, and that is ultra-cold atoms. This is a cloud of lithium-6 atoms. This is taken from my lab, but there are hundreds of labs around the world where people routinely trap atoms in a vacuum chamber and cool them down using lasers to ultra-low temperatures near the absolute zero. This is at a few hundred microkelvin. The cloud is here, and all the rest is just scattered light. Certainly, laser cooling is a remarkably successful method. It works. When it works, it allows one to take room temperature atoms and bring them down to millikelvin, microkelvin, and then ultimately physicists have been able to reach the ultimate, which is degenerate quantum gases, Bose-Einstein condensate, degenerate Fermi gases, by other methods such as evaporative cooling. So it's really been, in a way, a remarkable path, starting about 40 years ago when laser cooling was first proposed in 1975. But my message to you today is that laser cooling is maybe not the end all. Maybe it has its limitations, and one can find a better method. And so let me try and tell you why I'm not happy with laser cooling. So when it works, it's great, but it only works on about 10 to 15% of the periodic table of elements. Why is that? It's because it requires a very simple atomic transition called a two-level transition, because laser cooling relies on the momentum imparted by a photon to an atom. You have to scatter a very large number of photons per atom in order to bring the atom to rest, around 10 to the 5 to 10 to the 6 photons per atom. That implies that the atom must have a very simple structure where it's excited to an upper state, but it spontaneously decays back to the same state. We call that a cycling transition. And unfortunately, most elements in the periodic table don't have that simple structure. So, in fact, to sharpen that point, the simplest atom in the periodic table, atomic hydrogen, is not amenable to laser cooling. Not because its structure is so complicated, but because we don't have a laser at that wavelength, Lyman alpha, 121 nanometers. But let's say, and people in my community say, look, we love the alkali atom, so leave us alone. Don't bother me about other atoms. I don't care about hydrogen. I don't want to hear about the other atoms. But then my argument to them would be, that's fine, but even if I look at the alkalis themselves, laser cooling has reached a limit. And that limit is not in temperature so much, because we can reach as close as you want to the absolute zero, but in flux. How many ultra-cold atoms can you produce per second? And that number has saturated after 30 years of effort at about 10 to the 9 atoms per second, billion atoms per second. The reason for that is simple. It has to do with density and optical density. If you think about laser cooling, the way it works is the way it's the interaction of a single atom with a laser. However, when you have a cloud of atoms and the density becomes too high, then you get what's called multiple scattering. That is, a photon that's absorbed by one atom then gets emitted and is reabsorbed by an adjacent atom, and this photon is passed around like a little ping pong in between all these atoms, and that causes a destabilization, it causes the cloud to blow apart. And that's why it couldn't work for large numbers.
Do the energy level splitting, are they affected by interactions with neighboring atoms, and wouldn't it cause a broadening of the transitions?
At these densities, no. And certainly at 10 to the 9 atoms per cc, atom-atom interactions are negligible or very small. But photon-mediated interactions are not small, and that's what's limited laser cooling. Now, why is flux important? Well, I could ask the same question about this laser pointer. Is flux important? Well, this is about a milliwatt. That's about 10 to the 16 photons per second. What if I told you that I have a laser pointer, but it only puts out a femtowatt? That would be 10 to the 4 photons per second. Well, it's important because you couldn't see it, for one thing. And it wouldn't be useful for anything. And I think laser cooling has reached a limit in number, in flux, which has stopped it from having impact on other fields, such as condensed matter, material science, nanoscience, etc. And so I want to argue that suppose one could find a way to significantly improve the flux of ultra-cold atoms. And so about 10 years ago, I posed this question. And that's what I want to try and answer in today's colloquium, at least for the first part of the talk. I'll just give you a hint. If the answer was no, I wouldn't be standing here. So I'm not going to tell you the whole story because that would take me the whole hour, and I want to talk about medicine in the last part of my talk. But I will talk about cooling and pose a question about, suppose we have this prototype of a particle in a box. And I'm not drawing in the particles, but imagine that they're there. They're bouncing around. Could we make a one-way wall for atoms? Now, one-way walls are an example of non-reciprocity. And actually, that's a very hot topic today in metamaterials. People are working on making one-way walls for light, one-way mirrors. And what that means in practice is I can see you, but you can't see me. And it's been think about as cloaking, Similarly, you could think about a one-way sound wall. I can hear you, but you can't hear me. Now, one can think of breaking reciprocity with light and sound, but here I'm talking about breaking reciprocity with atoms themselves. In other words, making something that would let the atoms go one way but not back. And why is that interesting for cooling? Well, if I could do that, this would allow me to cool the atoms in the following sense. Suppose I have atoms equally distributed on both sides, but this wall is a one-way wall, which means that the particles on this side can go through, but they can't come back. Well, then if I just wait, all my particles will now accumulate on this half, and now I could just take this wall like a piston and expand it adiabatically, and the particles inside will cool, and I'm going to return to my original distribution, but at a lower temperature. So it's clear that if I can make such a one-way wall, I can cool. And we proposed this, actually, about a little over 10 years ago in a conceptual paper, which eventually got published. It actually ran into some difficulties with referee A, who I hope is not in the audience, who gave all kinds of reasons why this could never work. And I answered with my co-authors all the complaints. In the next round, they sent it back to the referee, and he said, now he believes that it works, but it's trivial. So then we finally argued with the editors and convinced them that it works and it's non-trivial, and it got published after over 9 months of arguing. But I want to illustrate how this works, because it actually is so simple that maybe after I explain it, you will say it's trivial. That's the danger of doing something too simple. The key elements to breaking reciprocity are a conservative potential. In our case, it will be a magnetic field for the atoms, and some irreversible process, which is optical pumping, which I have to define. So let me switch to that and explain the toolbox. So So these are the tools that we have at our disposal when we want to control atoms. The first tool is what is known as optical pumping, invented by Alfred Kastler, who got the Nobel Prize in Physics in 1966. So Kastler imagined a beam of atoms coming from a source, and I'm sorry for this picture, it looks like a little bit busy, but imagine you have some atoms emanating in slightly different angles, but mostly collimated, and you illuminate them with a laser beam, which we call the pump laser, which has a particular polarization. Let's consider a case where the atom has a magnetic spin 1 in this case. So we have +1 state, -1, and 0 in the ground state. And then we have some excited state. Let's say it's also spin 1. Initially, out of the oven, the atom is an equal statistical distribution of all three states. And these states control how the atom responds to an external magnetic field. In this plus state, it sees the field as a repulsive barrier. In the 0 state, it doesn't see the field at all. And in the -1, it is attracted to the field. So we can drastically change the response of an atom to an external magnetic field just by controlling which state we're in. And Kastler showed that if you use the right polarization, in this case circular polarization, and use the selection rule that tells you that when it absorbs a photon, it must increase its number, delta m, by +1, that means from -1 it goes to 0. Now from 0 it can decay back to the original 1, or it can decay down to 0. In the 0 state, it again absorbs a photon and goes to +1. Now if +1, it can go back here, but then it gets another chance, or it decays into the +1. But once it's in the +1 state, there's nowhere for it to go, so it gets stuck, it accumulates. And that is what we call optical pumping. So that means that after several cycles of absorption and emission, you've now taken the atoms, all the atoms, and put them into a desired magnetic state. Now we can do that at will. We can, by changing the polarization, we can either put them in the +1 state, or we could optically pump them into the 0 state by using linearly polarized light instead of circularly polarized light, and using the selection rule that 0 to 0 transition is forbidden. Okay, so how do we use that tool to make a one-way wall, non-reciprocal wall for atoms? So let's imagine that we have atoms and they're all prepared, all optically pumped in the m = 0 state in this box. Let's turn on a magnetic field in the center. What happens to the atoms? Nothing. They don't see it because they're m = 0 state, so they don't respond to the magnetic field. They can move back and forth as if it's not there. But now let me break the symmetry by turning on this red line, which indicates a laser beam that is optically pumping, able to optically pump any atom that crosses it, will be optically pumped from m = 0 to m = 1 as it crosses that beam. Now what's going to happen? Atoms on this side, if they're moving in this direction, they will first go through the field, they don't see it. But then they'll encounter this laser beam which pumps them into the m = 1 state. Now they're converted to a m = 1 atom. If they try to come back, they encounter the field, which is a repulsive barrier, and they can't get through it if it's strong enough. So that means that any atom here will go through, but it can't come back. What about atoms that are here? Well, before they hit the wall, they have to cross this optical pumping beam, so they're pumped into the m = 1 state, and then they can't. Then they're turned back. So the end result is that all the atoms here are going to be moved over to this side of the box. Well, so this is the idea. It was a toy model in 1 dimension, so being an experimentalist, and I have to now take this from this toy model and go to real life, which is 3 dimensions and laboratory, etc. So we demonstrated this kind of cooling with a one-way wall and showed in a series of papers, the first one was Fissure Letter in 2008 and several subsequent publications, that we were able to substantially cool the atoms. I haven't defined phase space density, so don't worry about it, but 350 times is a big effect. Take my word for it. So, interestingly now, what would Maxwell say, and how does this relate to Maxwell's demon? So normally I could just imagine what Maxwell would say, but it turns out that Maxwell had wrote a lot of letters, and these weren't emails that could be deleted easily. So there was a record And he sent a letter to his friend, another friend, Lord Rayleigh. So he had good friends, Lord Kelvin, now Lord Rayleigh. And in that letter to Lord Rayleigh, he said, I do not see why even intelligence might not be dispensed with, and the thing made self-acting, allowing all particles going in one direction while stopping all those going the other way. So Maxwell's idea was that you don't need an intelligent creature, a demon. You just need an automatic, self-acting one-way wall, which is what we have constructed. So I think he would say this is what he was thinking of. It certainly accomplishes exactly what he had in mind. And now you might wonder or worry, why are we not violating the second law of thermodynamics, right? Because this is the concern. And the answer is that you can account for where the entropy is going. The entropy of the gas is going down, clearly, because we are concentrating in a smaller volume. But there must be a sink for that entropy, and the answer is it's in the scattered photons from the laser beam. So if you think about a laser as a source of zero entropy photons, very ordered, they're all in one direction. But when an atom crosses it and gets optically pumped, it scatters photons into 4 pi steradians, and you can actually calculate that entropy. And I did that little calculation with some theorist colleagues in Spain, and we published a small paper on this, which shows that the entropy increase of the photon field compensates for the entropy decrease of our gas. So if you consider the complete system to be the atoms plus the laser, there is no violation of the second law.
Does that match exactly, or?
Very close to being exactly, yes. Yeah. It's all kind of we're doing the minimum that is required. Okay. Yeah. But what's important here, it is that we don't need this intelligent creature, and I think that has taken the spookiness out of Maxwell's demon. We don't need an advanced measurement. That's why people doubted this could be done, because it seemed like you had to know in advance where the particle is going to go and then open a trap door. Even today, 140 years later, I think we can't do that. That's still impossible to us. But the nice thing is we don't have to. We can just make a self-acting device. So yeah.
I mean, isn't the whole situation that you describe simple from that viewpoint, that you look at the law of thermodynamics, and the laws of thermodynamics pertain to the situation of thermodynamic equilibrium, and now you drive a process by means of the optical pumping, which is a thermodynamic non-equilibrium process. You're in a you may be in a steady state, but you're not in an equilibrium.
Well,
and so there is no violation of the laws of thermodynamics when
True.
when you lower your entropy. Overall, of course, what you do is you pump entropy out of your system by applying a laser into your system.
True enough. I mean, certainly. I'm teaching actually thermodynamics and statistical mechanics this semester, and I'm always amazed at how well it works, considering that it really only applies to thermal equilibrium. But nevertheless, and you're right that the distribution that we're creating on one side doesn't have to be in thermal, in a sense, doesn't have to be in thermal equilibrium. But nevertheless, the fact that one can do this is still important.
But I would compare this unidirectional wall with a diode in a PN junction.
Well, not quite. I mean, optical diodes do. We can have that discussion later.
Because diodes work because they operate in thermal non-equilibrium.
Yeah. Okay. Well, maybe we'll postpone to the end. But
Okay.
the point is, what's important is that you have a closed system that you can reset and continue the cycle. It's not just a one pass thing necessarily. So it's important that you actually be able to build this into an actual repetitive cycle. So like an engine that has to come back to the starting point and you can start over again. So nevertheless, the point is that this is a way to cool atoms. So what we have is we've developed a set of methods, and the set of methods is summarized in a review article that I wrote for Science about 7 years ago now, but also in a more popular article in Scientific American, and you can download both if you go to my group website. Just look Raizen Laboratory. You look under publications. You can find these papers. The solution that we proposed, which has been experimentally proven at each stage is a combination of methods. One is consists of a magnetic decelerator, which I haven't discussed, and I don't have time to discuss in detail here, but it's a way to take atoms and slow them or stop them magnetically, just with pulsed magnetic fields. The other is this further cooling, which we call single photon or Maxwell-Demon cooling, which allows one to further cool the particles. But here's the bottom line. This is our expected performance, and we hope within the next year or two to actually prove this experimentally. But based on everything we've done so far, we think that these are realistic parameters, that in a single shot we will deliver ultra-cold alkali atom, lithium in our case, at a single shot of 3 × 10⁻13 atoms, which for our system is a pulse system at a 30 Hertz repetition rate would be about 10⁻15 atoms per second. And that's at the same conditions, phase space density, which essentially amounts to temperature and density of laser-cooled atoms. That would be a factor of 1,000,000 times better than laser cooling in terms of flux. So this is a big factor. Where we are right now today is unpublished result is this number right now is about 10⁻12 atoms. And we're doing this right now at 1 Hertz. So we are still well below, but we are optimistic that we can get higher, because even at 10⁻12 atoms per shot, we are far from saturating the carrier gas, which in our case will be helium atoms. And that already is about 1,000 times better than laser cooling in terms of flux. So there's a lot of room to improve, but it's clear, I think to me, it's clear that these methods will far surpass laser cooling for neutral atoms, because we don't have the limitation of this strongly interacting atom photon.
But there is another limitation. The ground state must be S = 1. The ground state of the atom must be S = 1.
Spin.
Not many atoms.
No, it doesn't have to be. Lithium is a doublet. It's an S state, but in strong field, it's a spin 1/2 system.
So you don't need S = 1.
No. In fact, you can work with atoms that in the ground state actually are like the alkaline earths have a 0 spin in the ground state, but you can optically pump them to a metastable state that has spin 1/2 or spin 1. You can get whatever spin you want. I would say this is applicable to most elements in the periodic table.
Question?
Yeah.
Of course, you can't get a pure lithium-6 sample. There are going to be some lithium-7s around.
Well, we're actually working here with lithium-7, but...
Oh, okay. Well, then you can't, the converse is you can't get that totally devoid of lithium-6. There'll be interactions between the 6s and the 7s.
Well, I would say we can get them isolated from lithium.
Not totally.
Well, we've done it in my lab to 99.95%, which is pretty good.
There's still going to be a limitation.
I think we can even do higher if that's a problem. I don't think that at the temperatures and these conditions of laser cooling, the spin statistics are not even important yet. Only when you reach near quantum degeneracy do spin statistics matter, whether it's boson or fermion, and then the collisional properties do become important. In our case, the ultimate limit are the atom-atom collisions. That's all that. Finally, that's the limiting factor on density, for example. Okay, so where do we see that this will be important? And I'll give examples from where we're going with this. Atomic physics. There are many experiments in basic atomic physics. Atom interferometry, where you use atom interference to measure, for example, rotations and accelerations, so it could be a inertial sensor, or it can be used to test the weak equivalence principle. Quantum simulation of many body physics, quantum chemistry. Specifically, what we're going to pursue in my group, we want to use lithium, ultra-cold lithium, as a refrigerant to cool atomic hydrogen, which atomic hydrogen has been very hard to trap and cool. Notably, the groups of Kleppner and Greytak at MIT, Valraud, and before that, Silvera in Amsterdam. But those experiments to my knowledge, are not continuing. So we plan to make ultra-cold hydrogen, actually make a Bose condensate of hydrogen. And an interesting measurement, which has not yet been performed, is to measure three-body association, how three hydrogen atoms that are not spin polarized combine to make hydrogen molecules. And this is a laboratory-based experiment, but it is important for simulation of early star formation in the universe, because there it's believed that the primordial hydrogen collapsed under gravity to reach densities where the hydrogen converted to molecular hydrogen, which allowed the stars to cool. And so I have astronomy colleagues who are interested in actually getting a laboratory measurement of this process. We are looking into the possibility of using lithium as a refrigerant for antihydrogen, and it hinges on a key calculation, which I have a colleague who is now doing this, and we are optimistic, but it's not yet finished, and that is that there are two competing processes. One are elastic collisions, which are important for thermalization, and the second is annihilation. When a lithium atom and an antihydrogen atom collide, you can annihilate. But if the elastic component dominates over annihilation, it may be possible to use this to cool antihydrogen. And people have trapped antihydrogen atoms, or anti-atoms, at CERN, but they want to do precision measurements on them, and that will only happen if they are ultra cold. And currently they are so hot that they really can't do any measurements, aside from saying that they did trap them. We are interested in studying many body dynamics, in particular quantum turbulence of Bose-Einstein condensates. And that is an interesting problem that up to date has not really been possible to the extent that one would like, because it's been limited by the size of the condensate. So imagine that the largest condensates to date have been about 10 to the 6 atoms. And we believe with these new set of methods that we ought to be able to get to perhaps 10 to the 10 to 10 to the 12 condensed atoms. So much, much larger condensates, which will allow us to study turbulence of vortices on many scales. Okay, so this is kind of halfway point roughly in my talk, and I want to switch gears and talk about kind of an unexpected road that we got into about 7 years ago, sort of like this one. And I don't know. I don't know. That's a good question. No one's ever asked me that. But it's somewhere. Anyway, for us it was an unexpected road, and it relates to something that looks at first sight to be completely different. It relates to the question of isotopes. So just to remind you, isotopes are versions of the same element where you're only changing the number of neutrons in the nucleus. As an example, everyone's familiar with carbon isotopes, the ones that occur naturally. 12 and 13 are stable. 14 has a very long half-life, but is strictly unstable. And they all have the same number of protons and electrons, but notice the different number of neutrons. Isotopes also refer to this AAA baseball team in Albuquerque, but I won't be talking about that anymore. Isotopes are almost identical, which means that they have nearly the same chemical and physical properties. And so the challenge of isotope separation dates back to the 1930s, and the machine that was invented by this man, Ernest Lawrence, was named the Calutron. And this actually was originally motivated by the Manhattan Project, the desire to separate uranium isotopes. Cal stands for California, U for uranium, and tron is tron, cyclotron, Calutron. The way this worked, this is a photograph of the Y12 Calutron at Oak Ridge. I can get a scale of the machine from the ladder here, which was decommissioned in the late 90s. The Calutron works by the following method. You start with an element that you vaporize in an oven, creating a neutral atomic beam, and you bombard that with electrons to form an ion source. And the ions are accelerated and then move into a region of large magnetic field where their bending radius depends on their charge to mass ratio. So the lighter isotopes bend here and are collected in this pocket, and the heavier isotope is collected in that pocket. Now, I say this is a modern Calutron because this was built about 1950, and amazingly, this technology has not changed. since then. So we have a technology that essentially has been frozen for the past 70 or so years. And I challenge you to find another technology or another product, or maybe Heinz ketchup might be a good one, but that has not changed in all this time, right? But a high-tech product. And this is also surprising. Now, the isotopes that I mentioned occur naturally, but we can take stable isotopes and transmute them into radioisotopes and that are useful. And this can be done in a cyclotron. This is a medical cyclotron, which you can find in many medical school or hospitals around the world. Probably they have them here, I would guess, at the Huntsman Cancer Institute. I'm not sure, but they almost have to, because some of the isotopes that are produced, like fluorine-18 from oxygen-18, has only, I believe, a 40-minute half-life. So you really have to produce it on site, and you can't transport it very far away. So a lot of PET scans for medical imaging use fluorine-18. Or nuclear reactors that have a flux of neutrons and activate by neutron capture. What I was not quite aware of 7 years ago, but now very much so, is how much isotopes are a great natural resource. And I should say that, by the way, the Calutron, after World War II, the Calutron was used for separation of isotopes throughout the periodic table, but uranium separation moved to the centrifuge, which actually that technology is highly evolved. So certainly in that's the one case where technology has advanced, and it's kind of a double-edged sword. So when you hear about isotope separation, people get nervous. But we're talking about a general purpose machine that would separate small-scale isotopes mostly for medicine. But what they're interesting for is cancer therapy, medical imaging, basic science, and so on. But what is surprising is that we face a supply crisis of enriched isotopes. So until the 90s, late 90s, the U.S. still produced stable isotopes through its Calutron at Oak Ridge. But that was decommissioned, and other Calutrons around the world were decommissioned as well. And they've been relying since then on inventories that were built up. Most of those inventories are now depleted, and we depend on almost all stable isotopes from the large Calutron facility, which is in Russia. And needless to say, that's a concern, especially given the age of those machines, which is 65 years at least, and the politics, the geopolitics with Russia, which means that the supply of these isotopes could be cut off at any time. So that really tells one that there's an urgent need for new methods. What we proposed is that this Maxwell demon concept could be applied to the challenge of isotope separation. We call this magnetically activated and guided isotope separation, or MAGIS, and suggested that this is a replacement for the Calutron. So when we come back to the toolbox, the same toolbox that I introduced for cooling, we can apply now to this problem. The first step, again, is optical pumping. We have a stream of atoms coming out of an oven. Instead of trying to ionize the atoms, which is hard, let's just optically pump them to a desired magnetic state. So let's put them into the +1 state. And suppose all the other atoms are either optically pumped into the other states, or maybe they're coming out of the oven all in the ground state, in the m=0 state, like an alkaline earth or like ytterbium. So the principle of MAGIS is actually quite simple, but the arguments about scalability required us to do a lot of work to convince the referees about this. But imagine that you have a source and collectors here. And you have magnets. These are permanent magnets, the same sort of magnets that you put on your refrigerator. They are arranged in a particular configuration called the Hallbach array. But all that means is that they maximize the magnetic field on one side. So they achieve a field of 1 to 2 Tesla on close to the magnet. And the point is that if you have a collector and there's no line of sight between the source and the collector, that means that an atom cannot travel in a straight line and reach your collector. The only way it can reach the collector is by going in a curved pathway. Now, the atoms that we optically pump, shown in the dark line, we optically pump them into a state that is repelled by the magnetic field. And notice as they're coming in this cartoon, they actually don't hit the wall. They are repelled before they get there, and now they're coming on a different trajectory, and they can reach our collector. Whereas the other atoms that we don't optically pump will crash into here. We put some liner that we can collect and throw away later. This actually is reminiscent of something that is long gone, but it's called the Historic Pointsman of the railways. This was a very important role in 19th century British Empire, where there was a person called the Pointsman. That Pointsman was responsible for switching the tracks. So if you had one train with goods and had to go this way, they would pull a lever and the train would go that way. Or a passenger train would be allowed to go this way. Obviously, if you get it wrong, something bad happens. And this is kind of ominous. Apparently this was from Latvia. When Pointsman has a cup of tea, that doesn't sound like a good idea to me, but Anyway, you can see the tracks. It turns out that from reading Maxwell's writings, he was inspired to think of Maxwell's demon by this picture of the pointsman, because he thought about the demon essentially as a pointsman who directs the tracks, who tells an atom, you go this way and you go that way. Irrespective of this picture, the method works, and it works in a way that satisfies certain criteria. I would say that the three criteria that you really want to satisfy are A, degree of enrichment. And how can we enrich something in a small machine? Well, the answer to that is why is this so much more efficient than the Calutron? First of all, in electron bombardment ionization, only about 1 atom in 10 to the 4 gets ionized. So it's a non-resonant process, so it's very inefficient, first of all. Secondly, you have to separate by charge to mass ratio. Well, charge is always the same. Masses are the same within a percent or so. So you don't have a very good way the only way you compensate is by making the machine very large. And then you have large trajectories and large magnetic fields. And that's why the energy cost is so high. Typically, a separated gram in the Calutron of certain rare isotopes can cost around $50,000 just in electricity. So they are very, very inefficient and energy hungry. The second thing you need is scalability. In other words, you have to show that you can produce interesting quantities of desired isotopes. And interesting depends on your target. If it's a medical isotopes, it's typically around a few moles per year, hundreds of grams per year. And finally, you want something which is very energy efficient, which I just argued. So we worked hard and published a paper, accepted finally and published in Nature Physics, but this was probably one of the hardest papers that we ever published, and the referees forced us, and my students especially, to go back to the lab and take another 8 months of measurements. But finally, they were convinced that we satisfy all three criteria. And it was published. We have a US patent that was issued in less than a year. And it was highlighted by the Nuclear Science Advisory Committee to the Department of Energy that this is the most promising alternative to the Calutron to date. So I think generally the community is starting to accept this. But now the question was, where do we go from here? Because in a way, when you're at a university with students, you publish papers and then you move on to the next project. But in this particular case, I felt that we have to go to the next step. And the next step means we have to build production machines. We actually have to take certain important isotopes for medicine and produce them. But I can't do that in a university environment for a number of reasons. It's just not a good use of university resources. It's not educational for the students, because this is maybe a lot of engineering. So I started a new entity outside university, and I called it the Pointsman Foundation. This is a non-for-profit research organization. It's so-called 501c3. it will use MAGIS as a starting point. It's not necessarily only going to be limited to that, but it will start with that to produce isotopes primarily for medicine. And there was a story about this, if you want to read more about this initiative, in the Physics Today September issue on page 22. There's a story about that. We have a board of directors, so we're just getting started really with this effort. Myself as chairman of the board. Steve Abrams is a medical doctor. He's director of the Dell Pediatric Research Institute at UT Austin. His interests are using stable isotopes, such as calcium and iron, to diagnose metabolic dysfunction. So how we metabolize these minerals is very important for our health. For example, a large fraction of about at least half of the world's children have iron deficiency. And so this is important to be able to diagnose. And that's been held back due to the very high cost of isotopes, of these stable isotopes. Peter Fox, also a medical doctor, is director of the Research Imaging Institute at UT Health Science Center in San Antonio. He's essentially into the field of medical imaging. So that's, isotopes are heavily used there. Joe Jurczyk is medical doctor, is director of hematologic malignancies section of Columbia University, hematology oncology. He's an expert in radioimmunotherapy with alpha and beta particle emitting radioisotopes, monoclonal antibody therapy, etc. Doug Stone is a long-standing colleague and friend who's chairman of the Applied Physics Department at Yale, who's just shown great interest and support for what we're doing. So we have an advisory board: Stephen Chu, former Secretary of Energy, Nobel laureate in physics; Raymond Orbach, former Undersecretary of Energy, Director of Office of Science, and now at UT Austin; and my former advisor and friend Steven Weinberg, who's put his name on this, Nobel Prize in Physics in 1979. Right now, the foundation is just getting started. We have a president, Kirk Dorius, who's a patent attorney by day, but he's been extremely good. He's actually originally from the Salt Lake area, but now based in Austin, and he's been leading our effort. Let me say a word about why this is so exciting. In the space of cancer therapy, there is great promise for targeted therapy. Targeted therapy in general means that you have some molecular agent, which could be a monoclonal antibody or something else, which is designed to find and attach to a cancer cell, because that cancer cell expresses a certain antigen and it attaches to it. And then if you can find then a payload to attach to that targeting molecule, that payload will go off like a smart bomb and kill the cells in that vicinity, or maybe just the cell itself. So the key element is the radioactive isotope. This is still, I would say, an untapped potential, because we haven't developed yet the ideal targeting molecules, and we haven't had at our disposal the right isotopes. By right isotopes, I mean isotopes that have either beta emitting or alpha emitter with reasonably short but half-lives of about a week, decay energies that mean that the distance traveled in tissue is less than a millimeter, submillimeter, perhaps some gamma emission that will allow imaging at the same time. And the targeting molecules have not been optimized either. And this is an era where we are entering potentially an era of precision medicine, where one can design much, much better targeting agents by use of more modern methods of polyclonal antibodies, etc. The example that we are excited about is lutetium-177, and that actually will be our starting point. This is lutetium is a lanthanide, rare earth. Lutetium-177 is a radioactive isotope. Again, it satisfies, this is what I would call a really good isotope, because it has a 1-week half-life, 1 millimeter range in tissue, a small branching ratio of the decays, which are gamma emissions, so you can image them, like, for example, technetium-99m, which is widely used for medical imaging. in the last 15 years, there's just been an explosion of interest and activity surrounding lutetium-177, multiple clinical trials in many medical centers, and just in the last few months, it was approved for therapy in Europe, and it's going to be fast-tracked in the US by FDA, most likely. The way you produce, there's two pathways to producing lutetium-177, but really one of them is the only acceptable way. There's the direct route is by taking lutetium-176 by neutron capture. It's called an N-gamma reaction, producing lutetium-177. Two problems with that is you also produce an undesirable nuclear isomer, 177M, and also there's no way to separate the desired isotope from the target material. So you have what's called very low specific activity. On the other hand, by starting from ytterbium-176, although the neutron cross-section is smaller, you're generating pure 177 ytterbium, which decays to 177 lutetium, and because they're chemically different, you can separate out the ytterbium, the lutetium from the ytterbium, and you make what's called carrier-free, very high specific activity, no contamination. So really, this is the only pharmaceutically acceptable method. But the problem is, again, I come back to the same issue, that the world supply, and that's shown here, this is the world supply today of ytterbium-176, and it all comes from Russia.
Where is it?
In my pocket? No. Well, I'd be happy if it was in my pocket because 1 gram costs $10,000. So 150 grams, that would be about $1.5 million in my pocket right now. But I could hold it in my pocket in principle. Actually, we bought these ingots from a company, and they are ytterbium, but they're not ytterbium-176. They're just natural ytterbium. So that is the challenge. And this whole field depends on this supply chain. So if this is disrupted, this therapy goes away. So that's why this is so important.
But what does supply mean? That means it's the currently enriched amount of material.
Yeah,
right.
But it's consumed because there's losses in the processing.
Right, so if all this is gone, then someone needs to get some centrifuges and try.
It's not a centrifuge element.
Okay.
There's no working gas. This cannot be separated by centrifuge.
Okay.
So that's a good point. This is only right now the only method of production is Calutron.
Okay.
But the good thing is that MAGIS is ideally suited to this element because ytterbium happens to have a zero magnetic moment in its ground state. So without a laser, it's non-magnetic, which means that we don't have to worry about all the 7 isotopes of ytterbium because they're not going to be affected by the magnetic field. It has a relatively low vapor pressure, about 1,000 Kelvin required for operation. It's non-toxic and has a convenient transition we can optically pump it to a long-lived metastable state that is paramagnetic. So all in all, our first goal will be to produce and sell ytterbium-176. I say sell because we're not a business, we're a nonprofit foundation, but by producing and selling these isotopes, we will be able to further the mission of the foundation. So we have a way to sustain our growth in in the longer term. It's exciting to consider an alpha emitter. Actinium-225 is a very promising alpha emitter and has been shown to be very effective, especially on dispersed cancers. Joe Jurczyk at Columbia has used actinium-225 to treat advanced stage 4 leukemia, and patients went into complete remission after this treatment. So, but the problem is, again, there's very few doses available. The National Lab, Los Alamos particularly, has worked on making actinium-225, but they have a separation problem, and that is that when they bombard a target of thorium with high energy protons, they are producing the actinium-225, which can be separated by radiochemistry, but at the same time, they're producing with the same cross-section actinium-227, which has a half-life of 21 years. So the good one you want is 10 days, but what do you do with the one that's 21 years? We don't know what the half-life or the lifetime in biological terms, but it's so long that it would almost for sure not be approved by FDA because the long-term effects of ingesting this alpha emitter into your body is unknown. So we believe we have actually done an analysis on MAGIS, and we believe that it could actually be done here as well. So I will end here, just on time. And this is our logo. This is the website, www.pointsman.org. As of today, we were just, we applied for funding, and it'll be announced, I think, next month, but we got a grant of about $3.5 million from one big foundation, and other foundations are coming in. So we believe by the end of the year, we will have about $5 million to jumpstart this effort, hire some PhD scientists in this laboratory outside of the university to actually start producing isotopes for medicine. So in summary, I started with Maxwell's demon, told you about cooling, about how we might learn how to control atoms, and about this application towards medicine, which I think is very exciting. So I'll end here, and thank you for your attention.
So is there some reason why you want a 503C and not a for-profit corporation?
Right. That was my question as well.
Well, actually, if you read the Physics Today article, you will find out that we also started a for-profit. But there's two rationales here. There's a class of isotopes that are very important, but they're not going to make a lot of money. And ytterbium probably falls into that class, and others like it, because you have to invest maybe $5 million to build up that laboratory, and we'll make an income of maybe $3 to $5 million a year. That may sound like a lot, but it doesn't get any investor excited. And so that's why the nonprofit is ideal for that, we feel. On the other hand, there are some isotopes, such as for lighting, mercury isotopes, like the lighting above your head, for which we think there could be $1 billion a year market. And that's for that we started a for-profit company. So, yeah.
Why is it so difficult to separate actinium-225 from 227? Maybe you could tell us a little bit about why.
Well, for one thing, it has to be done inside a hot cell.
Inside of what?
Inside a hot cell. And that sort of separation has never been done. We think and the other thing is there's not a lot of spectroscopic data on actinium. I mean, we found whatever is available, we have found and analyzed, but there's uncertainties in transition probabilities and such. So just being able to do spectroscopy to verify optical pumping, whereas in stable elements like ytterbium, that's all been worked out. So and this is going to have to be done at a national lab. So just for those reasons, otherwise it's going to be a piece of cake.
Well, 227 is obviously very stable.
227 is stable, so I mean for 21-year half-life. So, but the handling is very difficult. It has gamma emission. It's very hot, so you cannot handle it in this is, and furthermore, it's a controlled material. This will never get outside of a DOE lab. So, I think the alpha emitters are enticing. They're promising, but they present issues that we don't have to deal with. With the beta emitters, the nice thing is we don't have to worry about any government regulation. Really, there's no issues in handling, and so especially because we will primarily be handling the stable precursor. We don't even have to deal with the radioisotope, but. We have at the UT Health Science Center, San Antonio has a fully equipped radiopharma lab that can produce radiopharmaceuticals, and they have hot cells that can handle everything. But actinium is just and radium are kind of in a different class. So I think that's going to be the difficulty. It'll depend, I think, critically on how much DOE will work with us on this. That's the question.
Why wouldn't they work with you?
I don't know. It's something called politics, I guess. I think it's not, DOE is, there's questions at DOE whether that should be their mission in producing, cancer therapy.
How about NIH? NCI?
Possibly. I mean, but right now it's all controlled at DOE. And there's a rare isotope facility at Michigan State University in East Lansing, and I visited there recently. And I hope we can, but it's going to be harder from the standpoint of doing separation inside a hot cell is something no one has ever attempted.
For things do you guys need more flux for?
Well, for more precise atom interferometers, when people talked in the early days of Bose condensation, they talked about the atom laser. The atom laser is a coherent beam of atoms. But that's where I brought the analogy with our laser of light, is that the highest flux atom laser today puts out a flux of about 10 to the 4 atoms per second. And that's not enough to do interesting things with it, like atom interferometry. Atom interferometry could be a remote sensor. It could be used for detecting gravity anomalies. There's potential applications. People even are using it to search for possible deviations from the weak equivalence principle by measuring interference of atoms of different isotopes to see whether there's an effect, whether atoms accumulate phases differently in free fall. In other words, do they all fall at the same rate? I think there's a lot of applications. But at this point, I think the first step will be to demonstrate that we have a much brighter source of atoms, and an alternative to laser cooling for neutral atoms, which has been the standard to date. This is a different way of doing things. But until I think in the end, we have to publish a paper where we say, okay, here's ultra cold lithium. Irrespective of how you get it, all that people want to know in the end is how many atoms do you have per second, and what's their temperature, and what's their density. And if I can outperform laser cooling by a big factor, I would say it's a better method. So, yeah.
But so coming back to the physical principle behind these selectivity mechanisms that you've discussed here today, what it comes down to is that your entire system is brought into a non-equilibrium state by driving some sort of steady-state non-equilibrium process. And then, of course, you may have sub-equilibria on the two sides of your wall. You form sub-equilibria, and that means actually the temperature from the equilibrium where you start goes down because of pumping, essentially.
Right.
Yeah. So because the analog, yes, I made that diode analog. I can think about another one with a unidirectional wall, and that's not by means of optical pumping, and that sounds dull, but my question is that an adequate comparison using mechanical pumping? Putting a turbo pump into the wall, then you also have basically a unidirectional selectivity, and that is then what's called adiabatic decompression.
Right. You could. And in some cases you do that, but it's not.
It's of course not for optical. Right. Yeah, it's not optical pumping.
It's a question of efficiency, and I think it's hard to be here. In our case, our efficiency is about 1 to a few photons per separated atom, whether it's separated or cooled atom, and that's an efficiency that's hard to beat. And energy efficiency is important in the end.
I'm just trying to make an analog to established processes.
Right.
Yeah.
So is there concern that the technology like this might create complications for nuclear proliferation?
Yeah, it's a good question, and I've thought about it quite a bit, and I even had a debate online, and it was published in the back page of the APS newsletter with Francis. His name escapes me right now, but the other person who I debated tried to argue that way, but I think we have shown convincingly that our method does not compete with the centrifuge, where the centrifuge works well. And I've discussed this with people starting with Steve Chu and the NSA and NNSA, not NSA. And I think they were convinced by my arguments to the point that if there were concerns about proliferation, our patent would have had a Secrecy Act applied to it, but none of that has happened. And DOE has been very open about this, so I think people generally accept that our method is very good when it comes down to separating a few moles per year of something, but not large quantities. And uranium presents a whole set of other complications that I think would not make it very attractive to NAGIS. But whenever you say the word isotope separation, people immediately worry about that. So it is a valid concern. But I think I'm not too worried about it.
If there are no more questions, we thank Mark again.
Well, I just don't think my president.
Continue with that particular word and then.
Well, it's not called an atom laser, but it's such a low flux that it has. Essentially, it's just a boson compensated is launched out.
Sorry, usual stuff.
Yeah, you can then manipulate it like you would light. I mean, you can reflect it. You can build.
Can you speak?
You can build an interferometer out of it.
So how do you speak?
How do you split it? Oh, you can use gratings. You can use diffraction from light.
The same tools.
Similar tools, yeah. But there are complications. I mean, the fact is, unlike light, photons do not interact with one another, but atoms do. And that actually presents some problems in the atom laser that cause decoherence because of atom-atom interactions. And so, but I think the main limiting factor to date has been that the flux has been too low to be interesting, to be useful for a lot of things.
But for laser, you to have this stimulated emission. Is it something like that exists? Is it atomic laser?
No, it's not. It's not. It's kind of a weak analogy. I mean, it's not. It certainly doesn't operate like a laser in the same sense. It's not. It's not a continuous thing. No, it's not. It's just. In that sense, it's not a very strong analogy, but people nevertheless made that analogy. I don't know if I.
They're coherent.
It's just in the end you can